In this video, I want to remind you of something that we've actually already seen in this course, and that is, although we didn't say it this way, the solution set of a homogeneous system of m linear equations in n unknowns is a subspace of Rn. What we've seen already is how to describe solution sets of linear systems, and you may have noticed in some of my previous videos that I kind of have trouble saying solution set. I want to say solution space because I just know from my own learning that the solution set of a homogeneous system actually is a subspace. Okay. So here's the proof. Right? First, we know that the solution set of this system is a subset of Rn, because if there's m equations and n unknowns, that means the matrix here A is m by n, and that vector x has n entries in it. Sorry, vector x, it's a column matrix, right? And the column matrix of zeros here is has m zeros in it. So x has n things, this zero has m things in it. So the x's are coming from Rn. So I know that I have that every solution is an element of Rn, so the solution set is in fact a subset of Rn. Now I just need to know that it's closed under scalar multiplication and vector addition, and let's prove those in the other order. So we got to show axiom 1 and 6. So let's take two vectors in the solution set. So take two vectors, x1 and x2, that I know when I stick them in here, multiply by the matrix A, I'm going to get 0 out. I want to show that the sum of those two also satisfies that. So when I add them up and then plug it in for x, that it multiplies to be the 0 vector. So here we go. Let's see what happens. If I take A times this, well, we know properties of matrix multiplication, and matrix multiplication distributes over matrix addition. So the A gets multiplied the first one, the A gets multiplied the second one, the results get added. But A times that first one is 0 because x1 is the solution to that equation. Likewise, A times x2 is equal to the 0 vector because x2 is a solution to that equation. And 0 plus 0, 0 vector plus 0 vector is the 0 vector, right? And so x1 plus x2 is a solution to ax equals 0. And we have that addition is closed in this set. Likewise, let k be any real number and take the same x1 we had up here. So x1 is a solution. And I look at k times x1 and say, is it a solution to that equation, right? Because I want to show that scalar multiplication is closed. So here we go. K times x1 multiplied by a. Again, I know algebraic properties of matrix multiplication, and this constant can be written out in front. But then a times x1 is equal to 0 because x1 is a solution to that equation, and k times the 0 vector is the 0 vector, and that's closed. Under scalar multiplication, we satisfy axioms 1 and 6. We are already a subset of Rn, and so I know I have a subspace of Rn. So let's just take a look at an example. Again, this is stuff we did so we did quite a bit earlier in the course. I've got a system here of 3 equations and 4 variables. Just in that itself, I can see it's a homogeneous system, and some theorems we had earlier on would tell me that I've got infinitely many solutions, right? Because I've got more variables than equations. So there's at least one free variable here, and in fact, it turns out that there's 2, I think. So here's the system written in matrix form, right? There's a 3 by 4 matrix. Just pointing out that there's 4 variables here, so this will be a subset of R4. The solution set is a subset of R4, and you're ending up with a 0, 0, 0 there. Making the augmented matrix, putting in reducer echelon form looks like this. Seeing that row of zeros on the bottom, that lets me know that I actually have 2 free variables. Right? I got 2 leading variables because there's 2 leading ones there, and then columns 3 and 4 don't have any leading ones, so they are my free variables. And so if I let x3 be s and x, that should be sub 4, equals t, then x1, solving this first equation, subtract the 4s, subtract the 5t over to the other side. Likewise, x2, subtract the 2s and the 3t over to the other side. x2 would be that. So this is the way we wrote it back earlier in the quarter. x1, x2, x3, x4 equals this, and we even subdivided it into something that looked like that. So everything that's got s's in it, there's a -4, there's a -2, there's a 1, and there's a 0 here. And likewise, all the stuff with t's in it, -5, -3, 0, 1. And I have that the set of solutions to this system of equations can be described as a linear combination of these two vectors. Something times this plus something times that vector. And we've seen now that this is actually describing a plane through the origin, right? And planes through the origin are subspaces of R whatever, in this case R4, because it's two vectors in R4. So I'm getting a subspace. As I said, this is not really new information. It's just a different way of looking at the results that we're getting.